Okay, I think we're ready now to try to do our first circuit. Now, before we can begin our first circuit, we do have to introduce just one more circuit element so that we can do this, right? We already have one element now, which is our wire, but we're going to need something to drive current down through our wire. So here I'm going to draw my wire. It's going to look something like this. Again, I'm going to draw it now vertically, but I'll have him coming down like so, right? My long square rectangular wire. And because now this is made out of some resistive medium, we typically call this thing actually as a circuit element a resistor. And we've just gone through the analysis and we know how current and voltage relate in the resistor. In fact, if I just peek up here a little bit, that was the Ohm's law that we have just been at some pains to derive. So that's my first element, but I'm going to need something to actually drive the current down through this resistor. And that new element, in addition to the resistor, is a battery. So here I'll kind of sketch for you a battery, right? Usually they're kind of cylindrical. You can imagine this as like some AAA battery you might have in a in kind of an old MP3 player that doesn't have a USB charger on it, right? So I've got a battery. They kind of look like a little cylinder with a wider end here on the bottom, and they typically have like a little nub here that attaches here on the top. And if you look carefully, there are signs associated with these. The little end with the nub on top, that's usually called the positive end. And the nub and the metal plate on the bottom, that is called the negative end of the battery. And now, the way a battery functions, we don't have time to get into all of the electrochemistry. It's actually fascinating. But long story short, what happens inside the battery is that there's an electrochemical reaction that's occurring. And that reaction actually does two things. It proceeds in a forward direction. It releases energy. And in the process of that energy release, it transports positive charges up from the bottom of the battery to the top of the battery. So very quickly, when you assemble the battery, the reaction begins to occur and you start to build up actually a collection of positive charges on the top terminal and negative charges on the bottom terminal. But as you might suspect, that can't go on forever. Eventually, I build up so many positive charges on top that it takes a good amount of energy actually to move the next charge up there. And eventually, the chemical reaction can no longer proceed. It stops exactly when the amount of chemical energy released matches the amount of work it takes, in other words, the voltage, right? The amount of work it takes to move a positive charge from the bottom side of the battery to the top side of the battery. The voltage then that the battery develops from its bottom end to its top end is just that chemical release energy divided by the amount of charge. So what you end up with is something that magically always has the same voltage difference, the same voltage going from the bottom of the battery to the top of the battery. It's determined by the chemical reaction, and the variable that's usually used to describe that voltage is this curly E. It's called the EMF that's associated with the battery. EMF that's associated with the battery. I wanted to erase my curly E. It didn't come out looking so good. Let me try again. You have a script E, something like that. Now, the way we can make a circuit, the way we can make things flow, is we can take a wire, right? And we're going to connect the wire from the top terminal of this battery to the top side of my resistive element, like so. And as you can imagine, these positive charges really hate each other. So if you give them a pathway, they're going to follow it, and they're going to move out this wire and start to occupy our conducting material over here. But as we pointed out very quickly, you'll end up with zero electric field inside there unless you're very careful to allow the charges to come off of it. So on the bottom face here, I'll kind of draw it in there, right, with dashed lines. I'll hook up another wire, and that wire I'm going to connect to the negative side of my battery so that now the positive charges that are flowing out the top of the battery can just go ahead and continue to flow down through my conducting material, across the bottom wire, back up into the battery, and the battery and the chemical reaction can pump them back up to the top of the battery again, and I get charges flowing around in a cycle like this, in other words, a circuit. Now, to analyze this, it helps to be able to draw some kind of a diagram, right? It's kind of hard to do the analysis if I'm always drawing these three-dimensional pictures. So there are certain standard symbols that are typically used to represent a circuit like this, and each element has its own symbol. So for instance, the battery symbol looks like two parallel lines, but one is longer than the other, and you label them plus and minus corresponding to the plus and minus signs of your battery, with again this curly E as the EMF. The voltage always maintained constant across the battery. The wires then are represented just by lines, kind of like in my physical diagram. The conducting material that's offering some resistance to the flow of electricity is indicated by a jaggedy line that kind of suggests it's hard or torturous for the charges to travel down along through here. And then finally, my other wire I can just draw as a line to complete my circuit. Now, to analyze this, it helps to consider various points in my circuit. There's going to be the point on the very top here of my battery where the charges are going to be leaving. I'm going to call that point A. There's going to be point B then where they enter into the conducting material, point C here on the bottom, and then point D here as they return to the bottom side of the battery. In my diagram schematically, I'll represent those points as A, B, C, and D. Now we can actually fairly quickly carry out our analysis. It turns out that in circuit analysis there are really two basic rules, and you already know them because you've been studying the fundamental physics of electricity. The first of these rules is Kirchhoff's current rule. So that's Kirchhoff. So Kirchhoff's current rule. And this you already know. Kirchhoff's current rule simply states that the current flowing into any region, because charge is conserved, right, must match the total current flowing out. In other words, the net flow in and out of any region in steady state must be zero. What that means then is that if I have this current I flowing down through my conducting material, or over here I might indicate it on my diagram like this, current I flowing down through that resistive medium, if I think about junction C, that means that this current I that's flowing into C must match the current I that's flowing out of C. So I know what's going down this wire down below also must be I. Similarly, as it goes through around this wire and enters the point D, the current going into D must match then the current flowing inside the battery. So the current I must also flow through the battery here in the upward direction. When it gets to point A, again, current I flowing into A must match the current I flowing out along this wire. So I would have a current I flowing out along there. And if you think about what we've just said, each element here, these two wires and the conducting material and the battery, they all just have this current I just all flowing right through them all the way around the circuit. In this case, the application actually of Kirchhoff's current rule was fairly simple. It just says that the current I has to be the same all throughout as the charges pump around the circuit. Otherwise, I'd be building up charge somewhere. In more complex situations, you'll see this will tell us a lot of more valuable, not obvious information. The second Kirchhoff's rule is Kirchhoff's voltage rule. And this then is the last key we need to solve this, our first circuit. So Kirchhoff's voltage rule. Now this voltage rule comes down to, in the end, just this property of path independence that we've been talking about for voltages and for work right, that we've been talking about from the beginning of this lecture. And what it says basically is that I can take any two paths, and the voltage to go around those paths will be independent of the particular path I chose. So there's a particular path that I'd like to choose. It might seem a little silly, but I'd like to consider the voltage going from point A to point A. Now, as you can see, there are really two ways to go about that. I could start here at A and take a piece of charge and just move it in a tiny loop, right, and just take it right back to A, moving essentially no distance. Now, if I do it that way, I think it's pretty clear if I'm not moving the charge over any distance, right, I'm just leaving it there basically, well, that's got to give me 0. The beauty of this, though, is that I can take a different path. Instead of just taking like this infinitesimal silly loop, I can go from A to A all the way around here through my circuit. And for that, then, I can use the property we had talked about in adding up work previously. If I want to go from A to A around this way, I can do it by first going from A to B, from B to C, C to D, and then D back to A. So the voltage from A to A is then going to equal the following sum. I will have the voltage then to get to B from A, plus the voltage to get to C from B, right, as I go down from B to C, plus then the voltage to get as I go from C to D, right, I'll get to D from C, and then that's C, and then finally, let's just get that down there for C. Try again here, D to C. And then finally, I can get from D back to A. Now, let's look at these terms individually. The voltage as I go from A to B. Well, here, notice I'm going across a wire. Now, the nice thing about a wire, if it's an ideal wire, a perfect conductor, is that we know there's no electric field inside if it's an ideal conductor. So then the voltage would have to be 0. Another way to see this is to think of this guy here as some kind of a resistor, right? It's going to be following our rule. It's some kind of a conducting material. It's going to be I times some resistance R. But because this is an ideal wire, we always assume the resistance of an ideal wire is 0. So that whole term will give me 0. But that's only because from B to A is an ideal wire. Then, if I look at the voltage going from from B to C, right, that is a perfect application now of what happens when I look at the voltage differences going through a conducting material. But when I go that way, I know from my previous analysis, right, that element is going to obey Ohm's law. So that will be I times R. But we have to be very careful here because we're dealing with voltages. And as we've been emphasizing, it depends on the order. It depends on how you wire up the particular circuit element. We're going from B to C, not from C to B. So this in principle could be a plus or a minus. We have to think about it very carefully to make sure we've gotten the right one. So we're going to come back to that term in a moment. Now, we go from C to D. I'm then just going along my ideal wire here. My ideal wire, again, is going to have 0 resistance. So I could write it as I times 0, which will be 0. And then finally, I'm going here from the negative side. I'm going from D up to A, like so. I'm going from the negative side of my battery up to the positive side of my battery. I know that means then the way the signs in the batteries work out, right? That is just the way I would wire a voltmeter in order to get a positive reading. If I'm going from the minus to the plus side of a battery, that comes up as a plus change in the potential, and that amount of potential is set by the EMF of the battery. So that's going to be a curly E. And then finally, I have to go from, that was from point D to point A. I've gotten myself back to point A. I've now completed here my analysis. Now, when I come to this resistive element, you'll notice I've gone, if I look at my direction, I'm going from B to C. I'm going down here in my diagram, or in this case, I'm starting at the top end of my resistor, right, and ending up at the bottom end. Now, inside that resistor, we know, particularly if you look at the flow of the current, right, the electric field inside here is pointing down. Notice that I'm going with the electric field, not against the electric field. If I'm going with the electric field, then remember the sign here is going to be the minus version of the sign. We had said previously at the very beginning of our discussions, when we were thinking about a capacitor, right, that the voltage is positive if you're going against the electric field, if you're going upstream. In our particular case here, sorry for scrolling around so much, right, we are going downstream. We are going along the direction of the electric field, so that has to come in with a minus sign. So if I tidy this whole thing up, I've just concluded here that I've got 0, and 0 must equal minus IR. Remember, this term is 0, so I've got minus IR plus 0, and then plus the EMF plus curly E. And this then is an equation I can solve for the current. I just put IR on the other side of this equation by adding it, and then to get the current I can divide by R, and I've solved now for the current through my conducting medium. When wired up to a battery, we have solved our first circuit and found the following nice and simple result.